Okay, it is 3:30, so I guess we can go ahead and get started. Sorry about the technical issues that we were experiencing on Tuesday. I do think that I have come up with a effective enough workaround, so hopefully we should not have any further issues, at the very least with me getting kicked out of the Zoom room. But again, if we do end up, if a scenario such as that happens again, I would say give me about 3 shots, if you will, to you know, enter the Zoom room again. I would say if I'm gone for more than 7 minutes, you guys can call it a day. Most likely, what I will be doing is frantically trying to get onto Canvas to send you guys a message, just letting you know what the situation is. But yeah, I think we should be, fingers crossed, good to go, and that we shouldn't have any major issues with that. But yeah, unfortunately, that is one of the downsides of doing the online teaching thing. So yeah, just a little bit of housekeeping before we jump back in. So we do have our first homework assignment that is going to be due tomorrow at 11:59 p.m. On Canvas. And again, generally speaking, for most of these assignments, there'll be 2 files that you'll end up submitting. One of them will be the Jupyter Notebook file, and then the other one will be some other file that you've used to, write your manual calculations. On the other hand, if you find that you are able to effectively communicate yourself, like in the markdown on, in that Jupyter Notebook file, that's totally fine if you want to do it there. But, the option is definitely open for you to write something by hand, take a picture, mark up a PDF, anything of the sort. Okay, so what we're going to do is hopefully finish up with this Unit 2, and I did post the Unit 3 materials this morning, so we might dig into that at the end of the class. But yeah, that's what we're going to do today. So yeah, any questions before we get started? Okie dokie. So what we're talking about here in Unit 2, if you recall, is basically giving a roadmap, if you will, of all of the different types of clustering algorithms that exist in the literature. Now, this roadmap is not really meant to be, completely comprehensive, for instance, of all the algorithms that exist, but more so it allows for us to break down the different types of clustering algorithms that exist in the literature. And one of the ways that we go about breaking down the different types of algorithms that might exist is talking about all of the variety of ways in which we might define what a cluster actually is. So for instance, we've been talking about a series of cluster definitions, and some of these definitions are going to be more effective than others when it comes to describing particular types of clusters that we can see like with our eyes. So for instance, we talked about a well-separated definition of a cluster, which is simply just, clouds of points that happen to be well separated from each other. But again, this begs the question, what does it mean for, 2 or more clusters to be well separated? Well, that is an answer that all of the different clustering algorithms that are based on this definition, seek to answer. They each have their own different definitions. Similarly, we talked about another type of cluster definition called a density-based cluster. And this, again, are the way that we define clusters in this case. Simply, a cluster is a set of observations, which are, or a set of a dense region of observations, if you will, that happen to be surrounded by a region of a lower, points that have a lower density. So we tend to think of these low density points as noise. But again, this also begs the question, well, how dense is dense enough for a set of observations to be considered a cluster? And again, this is, a question that a variety of different algorithms seek to answer, each with, different results, each with different levels of success for different types of data sets that we might be looking at. And so the third type of cluster definition that we were exploring is what we call a graph-based cluster definition. And we discussed that a contiguity-based cluster is a type of graph-based cluster. So for instance, we can see that these 2 clusters here, the orange one and the blue one, would fit under the rubric, ideally, of a graph-based cluster. So for instance, we can see that these two clusters are not well separated. So if we're using a well separated based clustering algorithm, that algorithm is not going to detect the two clusters that we see with our eyes. On the other hand, if we were to define 2 points as being connected, if either they are 0.25 distance away from each other, or they form, or you can basically reach it in a connected path of points that are 0.25 away from each other, then this definition actually would enable us to, clearly define the two clusters that we see here. And therefore, a clustering algorithm that is based on this definition would, in fact, be able to identify these two clusters. So we can already get a sense that k-means, which is not a graph-based clustering algorithm, is not going to be able to identify these two clusters. But what we're doing here is we're trying to explore why that is. Why is k-means going to fail? And this is also going to be helpful for your homework assignment as well. So to think about why k-means would fail, we would first want to think about, well, where, if we were to take the mean of this orange cluster and this blue cluster, where would those two means be? Again, we're simply just taking the average of the, sets of x and y values of the orange points. So that would be a mean like we drew there. Oh, sorry. That should be closer to here. And then the blue mean would be some point closer to here. Okay. And so then we would want to think about, well, okay, if these two means that we just drew were our centroids, would we expect the k-means clustering algorithm to stop? So basically, would these be the final location of the centroids? Or is it possible that the centroids would move? So let me ask that in a poll. So the question is, do you think that the centroids would move in the next iteration of k-means? Yes or no? Okay. We'll give it a few more seconds. All right, so the majority of us say yes, and I'm going to say yes as well. So again, you want to remember in k-means, one of the steps that we complete in each iteration is the cluster assignment step. And so what we do in the cluster assignment step is we assign each point to its closest centroid. So what would end up happening here is we would actually end up getting, like for instance, these blue points here would be assigned to this orange, or the current orange centroid. And similarly, these orange points here would end up getting reassigned to this blue centroid here. So because of that, we're actually going to get a clustering that is different than this current clustering that we're looking at. So that might look something like this, that simply just splits the data in half. And then if we were to recalculate the average or the centroids of these two current clusterings that we're looking at, 1 and 2, then that would put our centroids in two slightly different locations, and therefore the algorithm would unfortunately not settle at the location of the centroids that give us the ultimate, that actually identify the two clusters that we're looking for. So basically we would say there are some points, I'd say some orange points that are closer to the blue cluster, the current blue cluster centroid. So they would get reassigned. Same thing for some blue points. They would get reassigned to the orange cluster in the cluster update step. Thus, the clusters would change, and thus the centroids would change. Okay. All right. Any questions on that? So unfortunately, because we cannot, it's not going to happen that the k-means clustering algorithm is not going to settle on these two centroid locations. So therefore, because of that, the k-means clustering algorithm would not stop at the clustering, which identifies the two clusters that we're actually looking for. Oh, I'm sorry. Yes, this should be no, my bad. Yeah, thank you. Switching my yeses and nos around here in the two questions I'm asking. Okay, so for starters, we do not believe that k-means is going to be able to identify these two clusters that we're looking for at all. And on top of that, we'd want to ask ourselves, well, okay, let's just say we were hoping to identify, number one, if the data set is clusterable in the first place. And number two, how many clusters actually exist in this data set? So my next question is, I'm going to put up a poll. Do we think that the k-means elbow plot method is going to be able to identify that this is a clusterable data set and that there are two clusters? All right. Okay, the definite majority for no. And yeah, so that's right. So you want to remember that the k-means elbow plot is only designed to detect the cluster number and the clustering structure for clusters or data sets that k-means is able to identify the clusters for. So in other words, it's only able to identify clusters that k-means is able to identify. So in all likelihood, the k-means elbow plot is going to look something like this. So that means, if you weren't actually able to take a look at the scatter plot with your eyes, you would be unsure as to whether there actually is a clustering relationship or whether it's simply just a clustering relationship that k-means is not able to identify. So based on this plot alone, it's either the case that there's no clustering relationship or it's a set of clusters that k-means is not good at identifying. So without any other, without any other inspection of other techniques, we wouldn't really know for sure. So we're going to actually test out our assumptions in just a second. So we're going to perform k-means on this data set. But at the end of the class, we're going to talk about a type of contiguity-based clustering algorithm, which is in fact able to identify two clusters such as this. So one such type of algorithm, we call that spectral clustering. And it's based on this notion of a cluster is a set of points that are all connected, essentially. Okay. Questions on that? All right, so let's go to the application and let's actually try out these assumptions. Okay, so we've seen all of this same code before in the previous example, so we're not going to go through the code in as much detail. But so yeah, this is the data set that we'd like to cluster. And so for starters, let's just assume that we actually know what the appropriate number of clusters to look for is. So we'll look for two clusters in k-means. All right. And so let's also extract the centroids of the two clusters that k-means finds. Okay. And so this, unfortunately, is the two clusters that k-means returns. Okay. And so we can kind of see why this happens to be the best clustering that k-means returns. Because basically, if we take a look at where the two centroids are, and we try to approximate what the overall inertia of that clustering might be, we do in fact get a sense that this actually would be the best location for these two centroids to go in order to keep that inertia as small as possible. On the other hand, if we had, if we'd actually been looking for k-means to identify, the two clusters that we're actually looking for, the inertia, what you're going to see, is going to be a lot larger, unfortunately. Okay, so because these clusters are not well separated and they're not spherical, k-means did not do well. And furthermore, let's test our assumption. Yeah. So let's test our assumption that the k-means elbow plot method is also going to be not effective. And so yeah, so this is what our k-means elbow plot looks like. We do not really see any type of strong elbow indicating that there are in fact two clusters. So yeah, so unfortunately the k-means elbow plot was not effective in this scenario as well. Okay. All right, any questions on that? All right, cool. So let's move on to another scenario or another type of cluster definition. So another type of way in which we might go about defining a cluster is what we call a prototype-based cluster definition. And so basically a prototype-based cluster is a set, or defines a cluster as a set of objects in which each object is closer or more similar to what we call a prototype of the cluster than to the prototype of any other cluster. Okay, so let's think about the k-means clustering algorithm. So what do we think here? Do we think that the k-means clustering algorithm is based on a prototype-based definition of a cluster, or is it based on one of these other cluster definitions that we've discussed? Okay, just give it a few more seconds. And if so, if you think that this is a prototype-based cluster, think about what that prototype might be. Okay, so most of us do in fact think that k-means does rely on a prototype-based definition of a cluster. So if that's the case, what is the prototype in k-means in particular? So in k-means, the distance metric that we're using is the squared Euclidean distance. But you want to remember the way that we go about creating a cluster in k-means is we assign each point to its closest centroid. So basically what that means is that each cluster, or each observation in a given cluster, is closer to its respective centroid than the centroid of any other cluster. So k-means is a prototype-based clustering algorithm. And in particular, for this algorithm, the prototype is the centroid, more specifically, the mean of the cluster. Okay, so we're going to talk about two other types of prototype-based cluster definitions in this class in just a second. Now, these algorithms are going to rely on a different prototype definition or a different representative of a particular cluster. So now let's think about what might happen, or so to kind of see the reason for why we might want to use a different prototype-based cluster definition. Let's take a look at this example here. So do we think that this data set meets all of the ideal properties of that the k-means clustering algorithm is designed for, or if not, which properties are violated? So question, does this data set violate any of those ideal properties? And if so, what property is violated? So I leave that for the chat. Yeah, so one of the properties that is violated. Yep. So there's actually two. So you can see here, there are these two clouds of points which are somewhat separated, but they're not well separated. So that's one of the issues. And there's actually another issue, which is going to be even more problematic. So I would say the sparsity is about the same. The sparsity is not going to be the major issue here. There's one additional violation. Yeah, exactly. So the big issue here, what we're going to see, is that it has outliers. So the answer is no. This is not the ideal type of data set. Oh, shoot, sorry. What happened? Okay, so let's, so you want to remember, uh-oh. Just because a data set does not have or does not meet all of the ideal properties does not necessarily mean that k-means won't be able to identify, what are you doing? All of the clusters that we're looking for. But in this case, maybe, what we're going to see is that perhaps the k-means clustering algorithm will not identify the two clusters that we're looking for. So let's just say, for instance, we don't really want this outlier to be considered a cluster by itself. Let's just say ideally we'd like to identify this cloud of points as a cluster and this cloud of points as a cluster. So ideally we'd like for the outlier to get lumped in with the closest main cluster that it's closest to. So the question is, so let's just say, for instance, that in a particular iteration of the k-means clustering algorithm, we had found ourselves in a scenario in which we had our two current centroids located here and here at the center of the two main clusters that we're looking for. So the question is, and I'll put this in a poll, do we think that this will be the final location of those centroids? Or do we think that the centroids are going to move in the next iteration? So yes or no, will the centroids stay in the same place? And if not, where do we think they're going to go? Okay, so most of us say no, the centroids will in fact end up moving in the next iteration. So where do we think they're going to go? Yeah, exactly. So we want to remember, like we learned in our early stats classes, the mean is not a summary statistic, or it's not a measure of center that is robust to outliers. So let's just say, for instance, these were our two current clusters that we had identified in our current iteration of k-means. Okay. And so the centroid update step would require us to calculate the mean of these two current clusters that we had. And so unfortunately, yeah, when we calculate the mean of the second cluster, because that mean is not going to be robust to outliers, this is going to be the location of the new centroid. And then centroid 1, in this particular case, would be still in the same location. Okay? Now, because of that, when we move on to the next iteration, our old centroids become our new centroids become the old centroids. Here's my old centroids. And so when we do the cluster reassignment step, unfortunately, now only half of the points in this main cluster here are going to be assigned to the old centroid too. And the other half is going to get assigned to this centroid here. So we can see that there's going to be this gradual process such that by the time that the algorithm finally stops, unfortunately, what we're going to end up seeing is that k-means is going to identify this single outlier as its own cluster, and it's going to lump these two main clusters together as a larger cluster, if you will. Okay, so just to answer my questions here, the answer is no. It's not going to end up in the same location because the mean is not robust to outliers, so it will get dragged in the the centroid 2 will get dragged in the direction of the outlier gradually. This will keep happening in each iteration until the algorithm identifies the single outlier as a cluster, and then everything else as the other cluster. Okay. So we're seeing problems in the presence of outliers when it comes to using the mean in particular as our prototype in this prototype-based algorithm of k-means. So can we think of a workaround here? Can we think of another prototype that we might use instead that may not have the same problem? So rather than using a k-means algorithm, what other type of summary statistic could we use? Like yeah, exactly. So rather than using k-means, we're going to introduce what we call the k-medians algorithm. So that's one potential idea. Use the median as the prototype instead of the mean. And you want to remember why we might do this is because the median, if we think back to our stat 101 classes or whatever, the median is more robust to outliers than the mean. Okay, so we're going to introduce the k-medians algorithm, but unfortunately, the k-medians algorithm is going to have a problem. Okay, so there are some downsides to k-medians, which we're going to talk about in just a second. So because of that, we're also going to introduce another summary statistic that is also robust to outliers, and we call that the metoid. But we'll circle back to that in a second. So let's explore the k-medians algorithm first, and let's talk about some of the pros and cons that it has. So before talking about the k-medians algorithm, much like we did with k-means, we're first going to introduce the k-medians optimization problem. So this looks very similar to k-means optimization problem, except what we're going to do is out of all possible clusterings with k clusters that can be made from a series of m objects in a data set, the k-medians optimization problem seeks to find the optimal clustering of k clusters that minimizes the sum. Now, technically, this sum, the distance metric that you could use in the optimization problem could be whatever you want, but I'm going to be more specific. I'm going to say the Manhattan distance or the L1 distance. So basically what we want to do in k-medians is find the clustering with k clusters that minimizes the sum of each object in the data set to the median of the cluster that that object was assigned to. So in this case, the median is going to be our centroid or our prototype. Okay. So So in other words, what we're trying to minimize here is this sum of the Manhattan or L1 norm distance of each point to its respective centroid. And if you've never seen the L1 norm before, the Manhattan distance, what you want to remember is it's not simply just the straight line distance from a given point to the given centroid. Rather, what it is it's basically you add up the x-axis distance from the point to the x-axis value of the centroid. And then you also add up the y-axis distance of the given point to the y value of the centroid. And basically, they call this the Manhattan distance because, like, if you've ever been to the city of Manhattan, you can never walk directly from one point to another. You always have to go like right on one street and then go up the other street. So the L1, so there's actually a wide variety of L1 or L2 or L3 types of norms. But basically what the L1, L2, L3, whatever types of norms refer to is the value, basically the exponent that you are raising the particular values to when you're summing them, essentially. So this is like the L2 norm. So the L2 norm is basically you would be squaring each of these absolute value sums. Like the L3 norm would be cubing each of these sums. So similarly, the L1 is you're simply just raising those absolute value sums to the 1, essentially. Okay. All right. Any questions on that? Okay, so this is the optimization problem. But again, like we saw with k-means, unfortunately, in all likelihood, there does not exist a fast algorithm which will tell you the global, which will find you the global minimum to this problem. So what we do instead is we use a heuristic algorithm that will converge to a local minimum to this function that we're trying to minimize. So this is how the k-medians algorithm works. So k-medians is going to look very similar to k-means, but do take note of some key differences here. So much like in k-means, we do need to specify the number of clusters that we're looking for. And again, we do need to make sure that the data set that we're clustering is completely comprised of numerical attributes. And so what we do in step 1, just like in k-means, we randomly initialize k centroids, basically within the range of observations in the data set. Okay. And next, just like k-means, we have our cluster assignment step, where we assign each point in the data set to its closest centroid. Now, here's going to be a key distinction. The distance metric that we are specifically using in k-medians has to be the Manhattan distance, or the L1 norm distance. Okay, we'll talk about why it has to be this way in just a second. And then we have the centroid update step, just like in k-means, where we find not the mean, but the median of each cluster that we created in step 2. And these medians are now the centroid. Okay. And just like in k-means, we have this stopping criterion, which simply just says if the old and the new centroids are the same, we stop the algorithm. Otherwise, we go back to step 2. Okay. I really want to focus on emphasizing this part in particular. We have to be very specific in the distance metric that we are using in this algorithm. Take note, this algorithm is only guaranteed to converge when we use the Manhattan distance in particular. Okay, and I want to say converge to a local minimum. Okay. Oh, questions on that? Okay. And so, yeah, this might be kind of a bummer. This constraint that we're placing upon the particular distance metric that we have to use. It may be the case that the Euclidean distance is actually a better distance metric for, determining the clusters that we're looking for. So we're going to discuss an additional prototype-based clustering algorithm in just a second. And we call this the K-medoids clustering algorithm, which actually has the nice property that you can actually use whatever distance metric that you want. Okay, but we'll talk about that in a second. So I want to first show you how you would use K-medians in Python. Okay, and how it might actually end up being effective when it comes to clustering this data set in particular. So first, let's actually see what K-means does. Let's validate our conjectures about what K-means is going to do. Okay, so we have this data set here. We see the outlier. So let's see what K-means does. So we'll cluster this data set with K-means, specifically looking for 2 clusters. All right, let's see what happened here. Okay. It's kind of hard to see, but if we're only looking for 2 clusters in K-means, we've got the one cluster here and the other cluster here. So we do see that our final centroids were here and here. Okay, so that's what we were expecting. So for starters, we can see that if we were only looking for 2 clusters, K-means did not identify the 2 main clusters that we were actually looking for in this case. Now let's take it a step further. Let's see what the K-means elbow plot would tell us. Is it going to give us any indication about how many clusters exist in this data set? Okay, now let me just skip over that here. So let's see what we find. Now, by taking a look at this elbow plot, how many clusters is the K-means elbow plot suggesting exist in the data set? 3, right, exactly. So this is actually not that bad. So what K-means is suggesting is that if you really want to extract the most meaningful number of clusters that it is designed to detect, then actually looking for 3 clusters might best serve you when it comes to your clustering goals, if you will. So let's actually take the advice of the K-means elbow plot, and let's use K-means looking for 3 clusters. So let's see what it does. Okay. So it does look like if we actually were okay with allowing this outlier to be a cluster by itself, then K-means actually did, in the end, identify the 2 main clusters that we were looking for. Now, based on your research goal, you may actually be okay with allowing for a single point to be considered to be a cluster. Or in other cases, as we're going to see in future units, you may actually not want your outliers to be in their own cluster. You may want your clustering algorithm to force outlier points to get lumped in with a much larger cluster of observations. Now, the thing here is if K-means was the only algorithm that you wanted to use, there's a couple of ad hoc things that you could do in the end. So, for instance, if you got a result such as this, you could have just said, okay, well, let's just do some post-processing. Let's assign this outlier cluster to like the closest centroid of one of the larger clusters. That's certainly something that you could do. On the other hand, you may not want to perform this, ad hoc, post-processing analysis. You might want the algorithm to directly, do this step for you. So in comes the use of another algorithm, such as K-medians or K-medoids. Okay, so we're not going to use K-medians because K-medians, unfortunately, like we mentioned, requires us to have to use the L1 norm as its distance metric. Oh, sorry, I have to reboot here for a second. So what we're going to use instead is another summary statistic that is also robust to outliers. And we call this summary statistic the metoid. Okay, so give me 1 second here. So someone's asking, why do we use L1 for the median method? So we don't have a lot of time to really go through the proof here in this class, but if you take a look at the corresponding book chapter in the resources on the first page of these notes, it does direct you to a proof, which basically indicates like why we have to use the squared Euclidean distance metric for k-means algorithm and why we need to use the L1 distance for k-medians. It basically shows that like we have to use those distance metrics in order for it to converge. But basically you want to think about like what would be the derivative of like a particular, or so you're essentially going to be using like taking derivatives of your objective function essentially. So take a look at that proof. I'd refer you to that. Okay, so where were we? So let's go back up here and let's introduce one more prototype. So we say in the context of clustering, we define what we call a metoid as an actual observation in the cluster in question, whose sum of the distances or sum of its distance to all other points in the cluster is minimal, or the smallest one. So for instance, let's just say we had a cluster like this, right? So if we were to use, if we were to calculate the mean of this cluster, again, because the mean is not robust to outliers, the mean is going to get dragged in the direction of, this centroid here, or this outlier here. But if we were to calculate the metoid of this cluster, let's see what that point is going to be. So basically, to calculate the metoid of a given cluster, what you would do is calculate a distance matrix for every set of observations in that cluster. And then you would take the sum of each column in that distance matrix. And so basically the sum of all the distances between A and then all the other points is this value here, so on and so forth. So what this shows us is that observation D actually has the smallest sum of distances to all other points in the data set. So because of that, what that means is observation D is in fact the metoid of this cluster. Okay, and so we can see that, because our observation, or because our metoid actually has to be an actual observation within the cluster, this allows for basically the summary statistic to select a point which is much more centrally located to the majority of non-outlier points within the cluster. So again, it's another measure of center that is more robust to outliers. So to recap, we have now discussed 3 potential prototype-based definitions of a cluster. We've talked about k-means, or in this case, the prototype that we're using is the mean. We've talked about k-medians, or in that case, the prototype was the median. And finally, we're going to introduce what we call the k-metoids clustering algorithm, where in this case, the prototype is the metoid. But generally speaking, each of these three prototype-based clustering algorithms is all going to, they're all going to be very similar in how they are designed. The two main distinctions that we're going to see is one, what is the distance metric that you use? And two, what is the prototype that you use? Okay. Any questions on that? All right. So without much ado, let's take a look at the K-menoids optimization problem as well as algorithm. Okay. So we define the K-menoids optimization problem in a very similar way. So we say out of all possible clusterings with K clusters that we can make with a set of M objects, our goal is to find the optimal clustering that minimizes the sum of each object to, in this case, the metoid of the cluster that the object is assigned to. So we call this metoid the centroid, okay? And take note, we can actually use, with K-metoids, any distance metric that we might want. So now this is the optimization problem. But the cool thing is, even when we move on to the heuristic algorithm, which hopes to find a local minimum to this function, what we're also going to see is that we can also use any distance metric that we want. Okay, so here's how the K-metoids clustering algorithm works. And again, this is a heuristic to the K-metoids optimization problem. It's not guaranteed to find the global minimum, but it is guaranteed to converge to a local minimum. So again, we need to specify the number of clusters that we want. And again, we need to make sure that our data set is purely comprised of numerical attributes. Okay. And just like K-means and K-medians, we have our centroid initialization step. Okay. Now, the way that the centroid initialization step operates is actually going to be slightly distinct from K-means and K-medians. So rather than randomly selecting a point, rather than randomly selecting K points that exist within the range of data set points, when randomly initializing your centroids for K-metoids, you actually have to select actual points that exist in the data set. So we say randomly select K actual points from your data set. Okay, so slight distinction. K-means and K-metoids. Okay, so do keep that in mind. However, step two, very much the same. So we have our cluster assignment step. And so this is where we would assign each observation in the data set to its closest centroid. All right. And the cool thing here is, just PS, you can use any distance metric that you want. So that's cool. All right. And much like we saw in K-means and K-medians, we also have our centroid update step. Okay. And rather than using the mean or the median, what we do is for each cluster from step two, we set the new centroids to be the point in the cluster that minimizes the sum of the distances within the cluster to that actual point. Or in other words, the centroid is equal to the metoid of the cluster. Okay. And finally, our stopping criterion is the same. So if our old centroid is different from our new centroid, if they're the same, then we stop the algorithm. Otherwise, we go back to step 2. Okay. All right. Any questions on that? Okay. So let's actually see how the K-metoids clustering algorithm might actually help us identify the 2 clusters that we're looking for here. And in particular, we want that outlier to actually get lumped in with this cluster here. So let's see if it actually works. So let's just say, for instance, we randomly initialized our 2 centroids. And again, we want to make sure that our 2 randomly initialized centroids are actual points in the data set. So let's just say we actually, we selected this point and this point to be our our starting centroids. This is our centroid 1, centroid 2. Now you want to remember, K-metoids can use any distance metric that we want. So let's choose to use the Euclidean distance for this algorithm. Okay, so the next step is we want to assign all points to its closest centroid. So all of these points would get assigned to this centroid. And all of these points would get assigned to this centroid. Okay. And then our next step is to calculate the medoid of each of these 2 respective clusters that we found. Okay. And again, you want to remember the medoid is the observation within a cluster that has the smallest sum of the distances to all other points within that cluster. So intuitively, you would think that the medoid is going to be the point in a given cluster that is the most centrally located. So that would be most likely this point here, roughly. Okay. And then the nice thing about this cluster here is that because we're essentially forced to pick a point within the cluster 2 to be our new centroid, this point is going to be much closer to the cloud of points, or the cloud of non-outlier points in this cluster here. So again, when we're picking our medoid for cluster 2, pretty much all of these points are going to be really far away from this outlier here. So nonetheless, or because of that, most likely our medoid, the point who has the smallest distances to all their points, most likely that medoid is also still going to be relatively well-centered within the main cloud of points. So my new centroid is going to be much more centrally located in cluster 2. Okay, so we move on to the next iteration because the old centroids and the new centroids are not the same. Okay, so we have our new centroid here, or excuse me, our old centroid here, and our old centroid here. Okay, then given that these old centroids are relatively well-centered, and perhaps maybe they are actually at the best, most well-centered point, what we see here is when we do our cluster assignment step, we're going to have these observations assigned to this centroid that they're closest to. We're going to have these observations assigned to this centroid that they're closest to. And so what we end up getting is essentially we have the same 2 clusters here. So when we recalculate the medoid, in all likelihood, we're actually going to end up with a medoid in the same set of locations. So old centroid 1 is probably going to be equal to new centroid 1, old centroid 2, is going to be equal to new centroid 2. Okay, so the old centroids and the new centroids are the same. And so therefore, we actually don't even need this third iteration. The algorithm stops, and we are in fact able to identify the two main clusters that we're looking for, and we're able to lump that outlier in with one of the larger clusters here. Okay. Yeah, any questions on that? Okay, so this was just our intuition, if you will, as to how the K-medoids clustering algorithm might work on this data set here based on how we know the algorithm works. So for good measure, let's actually apply K-medoids on this particular data set. So unfortunately, K-medoids is not contained in the scikit-learn package. So in order to use the K-medoids function, you will need to run this in your Anaconda command prompt to install an additional package, which we call scikit-learn extra. And the nice thing is that scikit-learn extra actually has a very similar syntax to scikit-learn. It's basically just adding on some additional clustering algorithms or machine learning algorithms that scikit-learn doesn't have itself. So what we can do is import this new package, and in particular, we're just going to import the K-medoids function. And the nice thing about K-medoids is that it operates, or it's, the syntax of the function is, for the most part, very similar to how the K-means function works. So, like we saw in K-means, first we instantiate the K-medoids function. We indicate the number of clusters that we want, and then we fit it with our data frame that we'd like to cluster. And again, just like in K-means, what that produces is this K-medoids object, which contains all the information that we would want to know about our resulting K-medoids clustering, including the cluster labels, which we are going to add as an additional column in my DF data frame called predicted cluster. Okay. And also, what I can do, just like in K-means, is I can extract the final centroids of my K-medoids clustering. So in this case, the centroids are going to be the medoids of each of my clusters. And again, I'll put those centroids, or my medoids, into its own data frame. Okay. And so when I plot both my cluster labels as well as my resulting medoids, great. It does look like, in fact, when only clustering the data set into two clusters, K-medoids was able to give me the result that I was looking for. Okay. All right, cool. Any questions on that? No? Okay. All right, so basically what we've been doing in this unit 2 is describing, again, a roadmap for all of the myriad of different clustering algorithms that might exist based on, number one, how we might go about defining what a cluster is. So another way that we might break down all of the different clustering algorithms that exist in the literature is based on the nature of the output. So what do the cluster rings look like themselves? Before I get to that, I forgot there was one additional thing that I wanted to say about K-medoids. So let's very quickly compare the benefits that K-medoids has over K-means. And let's compare some of the benefits that K-means has over K-medoids. So based on everything that we've said so far, what is one benefit that we've seen that K-medoids has over K-means? Mhm. Yeah, so we see one benefit is that K-metoids is more robust to outliers. Okay, so that was one potential benefit, but we actually identified another benefit as well. So can anybody think of what that other one was? Um, yeah, so it's an actual data point. So that fact kind of ties into why K-metoids is more robust to outliers. Yeah, it's more flexible. And why? Why is K-metoids more flexible? So we're going to remember, yeah, so K-metoids is guaranteed to converge to the local minimum when using any distance metric that you want. On the other hand, K-means has to use specifically the squared Euclidean distance in order to converge. Okay, the K-metoids is more flexible with respect to the distance metric. However, there is one downside or a computational downside, I guess I guess you could say, to K-metoids. So basically, when you are calculating the metoid as opposed to the mean, this metoid calculation actually requires more computational work than it requires to calculate the mean of a cluster. So because of that, K-means is more computationally efficient than K-metoids. So in particular, if you're familiar with computational complexity notation, the computational complexity of K-means is equal to a runtime, which runs in the order of the number of observations in the data set times the number of attributes in the data set times the number of clusters times the number of iterations that the algorithm actually uses. And so the runtime of K-metoids is going to look very similar. Unfortunately, because of the extra computational work involved in calculating the metoid in each step, the runtime actually requires us to consider, we essentially need to consider squaring the number of observations in the data set. Okay. So basically, if you have a lot of time to run your algorithm, you might consider K-metoids if you are concerned that your data set has a lot of outliers, or you'd like to use perhaps a distance metric other than the squared Euclidean distance. Okay. Great. Questions on that? All right. So as we discussed, one of the key ways of breaking up all of the different clustering algorithms that exist is going to be based on, again, the way in which you might define a cluster. But another way to break up, dictate the number of, different types of clustering algorithms that exist is also the type of output that you might get from your clustering algorithm. So we've already looked at, so basically all of the clustering algorithms that we've talked about so far are what we call partitional clustering algorithms. So this applies to K-means, K-medians, and K-prototype, or excuse me, K-metoids. And these are algorithms in which your final result of the algorithm is a division of a set of objects into K subsets or clusters, such that each object in the data set is assigned to one and only one subset or cluster. Or in other words, your cluster ring is a partition. Okay, so you can't have an observation assigned to multiple clusters. You can't have like every observation has to belong to a cluster. So basically, a partitional clustering simply just gives you one breakdown of the data. Now, this is in contrast to what we call a hierarchical clustering. So a hierarchical clustering algorithm actually returns multiple partitions or multiple clusterings of the data set. And in particular, we allow for these clusters that we're identifying to showcase what we call nested subcluster relationships. So the way that we display the nested subclustering relationships is in what we call a dendrogram tree. And basically, this dendrogram actually allows for us to not just cluster the data set once, but actually showcase this nested cluster relationship that allows for us to determine, for instance, which objects and which clusters are closer to each other than others. So let's look at a scenario in which we might actually find a hierarchical clustering algorithm useful. So let's just take a look at this data set here. So based on what we see with our eyes, how many clusters exist in this data set? So what do you guys think? What's a good number? Yeah. Yeah, it's hard to really be convinced that 3 is not the best answer. You know, you can clearly see 3 distinct clusters and only 3 distinct clusters with our eyes. Okay. Now let's just say we were to look at this data set here. So what do we think? How many clusters does this data set have? Some people are saying 4. So is there any less, are we a little bit less certain, perhaps, about how many clusters this data set has versus how many clusters, this data set has? Yeah, and it looks like we are. So some people are saying 2, some people are saying 4, some people are saying 5. And so essentially what we're seeing here, because of this uncertainty, is a nested subcluster relationship. So for instance, we might say that, okay, now I see these 2 clouds of points here, which are very well separated from each other. So you might say there's 2 clusters in this data set. But if we were to examine each of these 2 clusters that we found here, we're finding some further smaller separations that exist. So we might further say that perhaps this cluster can be broken down into 2. And same thing here, this cluster could be broken down into 2. And then furthermore, if we examine like maybe this cluster here, you might even further say that this cluster could be broken down into 2 based on this smaller separation. And maybe this cluster could be further broken down into 2. So these are all relationships that the dendrogram can actually tell us. So for instance, the way that we interpret a dendrogram is by drawing a horizontal line in the tree. So let's just say I decided to draw my line here. So to identify the corresponding clustering that this horizontal line showcases, you find all of the locations that this horizontal line intersects the tree. And then you basically follow the tree down to the set of points that show up on the x-axis. So basically we can see that this horizontal intersection has in fact identified 2 clusters. So this cluster of blue points and green points here, and this cluster of red and purple points here. But let's just say we wanted to draw our horizontal line in a different location. So let's just say we drew it here. So again, what we would do is we would find all of the locations that this horizontal line intersected the tree. And we would follow the tree down to the corresponding observations on the x-axis. And so what this, or the clustering that's represented by this horizontal line intersection, is the one that creates 4 clusters. So basically these subclusters within the 2 main clusters. So in other words, it identifies the blue cluster, the green cluster, the purple, and the red. And we can furthermore keep going down the tree all the way down to the bottom if that's what we wanted to do, in which in which every single observation was by itself in its own singleton cluster. Now that's usually not the most informative clustering. So we usually tend to stop higher up on the tree. But essentially what this showcases is a series of nested clusters in which the further you go down the tree, what you end up seeing is that each of your existing clusters will split into 2 gradually until they're all apart in distinct singleton clusters. I'm seeing a question. So this graph is useful for finding out the optimal number of clusters based on a threshold similarity value. Yeah, so you could interpret this dendrogram tree as another way of perhaps indicating what the inherent number of clusters might be. So for instance, if I were to create a dendrogram for this data set, what that tree would look like, most likely, is going to be something like this, where like all of the pink points are all merging with each other at a pretty low value. All of the yellow points are merging with each other at pretty low thresholds. And all of the, what's that color, purple points are all merging with each other at pretty low thresholds. And then, yeah, the merging that happens for the sets of pink, yellow, and purple points is going to happen at a much higher threshold. So when we move on to Unit 5, we'll talk about, how that threshold for merging or splitting is actually determined, because there's a variety of ways that you go about doing it. But yeah, essentially this proximity, or this y-axis value, essentially gives you an indication as to how far away each of these respective clusters are from each other. So if you see that, for instance, these clusters are, comparatively, further away from each other, this can indicate to you as well that, yeah, perhaps there are in fact 3 clusters or 3 inherent clusters that exist in the data set. Okay, yeah, so that's a good question. Any other questions? Okay, so that highlights the difference between a partitional clustering algorithm, which is simply just a single clustering, versus a hierarchical clustering algorithm, which allows for you to essentially create many partitional clusterings, each of which are nested within each other. Or in other words, these partitional clusterings are created in which we iteratively split one cluster at a time until they're all apart in their own singleton observation clusters. Okay, excuse me. So the final distinction that I'd like to make that kind of dictates a variety of different clustering algorithms that might exist is also going to be based on the nature of the output of the algorithm itself. So one type of output, or one type of clustering algorithm, is one that returns what we call an exclusive clustering. And this is one very much like the partitional clustering, in which every observation is assigned to one and only one cluster. So again, this is equivalent to a partition clustering. Now, this is actually in contrast to what we call an overlapping clustering. And this is one in which the clustering algorithm can actually allow for an object to be assigned to more than one cluster. So this is an example of an overlapping clustering here, in which not every observation is assigned to multiple clusters, but we do see that there there could be. There are, in fact, some observations that are assigned to multiple clusters. Okay, so we're not going to do too much with overlapping clusterings, but it is a type that exists out there. But another type of clustering algorithm that we are going to put a lot of focus on in this class is what we call a fuzzy clustering. Now, this is in contrast to an exclusive clustering. So this is basically the opposite end of the spectrum, in which in a fuzzy clustering, every object belongs to every cluster with some sort of membership weight. Okay, so let's just say we have 5 observations in our data set here, and we decide to look for 2 clusters. And so basically, every observation is assigned to some extent to every one of these 2 clusters in the data set. So we usually call this the cluster membership weight for a given observation. And usually these weights will range between 0 and 1. So if the weight is a 0, essentially what that means is that that particular observation does not belong to that cluster at all. And if the observation is assigned a cluster membership weight of 1, that means that it completely belongs to that cluster. And so furthermore, we usually represent these fuzzy clustering membership weights in a way, basically, in which the sum of the weights for a given object should all add up to 1. So in other words, you can think of each of these rows in your fuzzy clustering membership matrix as basically a probability distribution. So basically the probability, for instance, that observation 1 belongs to cluster 1 is 33%. And this could be a really insightful or a more insightful result, in particular when we're looking at, for instance, data sets that are not well separated from each other. So let's take a look at, for instance, observation B in this data set here. So observation B, as well as observation C, are what we call straddle nodes within a given data set or a given, clustering structure. And that, now while technically we can see in this clustering here, observation B happened to be assigned to cluster 2, but we can see that basically observation B actually, straddles these 2 clusters here. So it doesn't really make a lot of sense to, definitively say, yes, observation B definitely should belong to cluster 2, because it's so close to the other cluster that, a more insightful clustering would say something along the lines of, observation B, 50% belongs to cluster 2 and 50% belongs to cluster 0. So a straddle node is a observation that, straddles membership between 2 or more clusters in a given clustering structure. Okay, so we're running out of time, so we only have 2 minutes left. So let's think about what a sensible fuzzy clustering membership matrix might look like, in particular for these objects A, B, and C. So if you wanted to most effectively reflect the extent to which observation A belonged to cluster 0, 1, and 2, what cluster membership scores would you give to object A? So in other words, what 3 numbers would you put here? So for observation A, it looks like you're saying that it should 50% belong to cluster 1, and then about 50% belong to cluster 2. Okay, yeah, I kind of figured it was probably looking at the other one. But yeah, observation A, yeah, definitely looks like it strongly belongs to this cluster two. Excuse me, cluster one. So to indicate that, we might give, yeah, a very strong cluster membership weight, cluster one, and very weak cluster membership weights to cluster 0 and 2. Yeah. And then, yeah, I think, Akash, yeah, so that, what you said corresponds, I think, to cluster B. So yeah, so cluster B looks like it about 50% belongs to cluster 0 and cluster 2. So to represent that, we might put something along the lines of, something close to 0.5 for cluster 0, something close to 0 for cluster 1, and something close to 0.5 for cluster 2. And then similarly, just to kind of wrap this up, it looks like observation C more or less equally belongs to all three clusters. So to represent that, we might put, 0.33, yada, yada, to cluster 0, 0.33 to cluster 1, and 0.33 to cluster 2. Okay. Yeah, so that basically concludes Unit 2. So I'll be asking you questions about this in the next homework assignments. Yeah, and we weren't able to get to the next unit, so we'll just kind of start that on Tuesday. But yeah, that's basically it. That kind of gives you a rough overview of all of the myriad of different types of clustering algorithms that we're going to explore in this class, and also those that exist in the literature. So yeah, that's basically it. Yeah, so we'll wrap there. I will stop recording.